Category theory provides a universal language for mathematics through objects and morphisms. Morphisms are arrows that represent relationships between objects. It studies the relationships between structures rather than the structures themselves. Its foundations include objects and morphisms, functors that map between categories, natural transformations, limits and collimates, and adjoint functors. For example, instead of studying individual groups, category theory examines all groups and the homomorphisms between them. This reveals patterns that appear across all mathematics. Advanced concepts include monoidal categories, enriched categories, and topoi, which serve as generalized set theories. Entire mathematical theories can be reformulated as categories. This allows insights to transfer from one domain to another through functorial relationships. Homotopy theory studies spaces through continuous deformations. These include stretching and bending without tearing or gluing. It focuses on properties that remain invariant under such transformations. Its foundations include homotopy groups that measure holes in spaces, fiber bundles, exact sequences, and spectral sequences for computing cohomology. A coffee mug and a donut are homotopy equivalent because each has exactly one hole. One can be continuously deformed into the other. Set theory serves as the axiomatic foundation of mathematics. It provides the formal language for defining all mathematical objects. Beyond basic operations, it explores the nature of infinity itself. Its foundations rest on Zermelo-Fraenkel set theory with the axiom of choice, denoted ZFC. It studies cardinal numbers that measure sizes of infinite sets and ordinal numbers that extend ordering into the transfinite. For example, Cantor's diagonal argument shows that real numbers R have strictly larger cardinality than natural numbers n. This establishes a hierarchy of infinities denoted by Aleph numbers. Advanced topics include forcing, which proves independence results. Large cardinal axioms extend set theory beyond standard models. Inner models and descriptive set theory analyze definable sets. These investigations probe the limits of mathematical truth. Certain questions transcend proof within established frameworks. Model theory analyzes mathematical structures through formal languages. It studies the relationships between theories and their models. Theories are collections of axioms. Models are structures where these statements hold true. Its foundations include first-order logic, satisfaction relations, elementary equivalence, compactness theorems, and quantifier elimination. The compactness theorem states that if every finite subset of sentences has a model, then the entire set has a model. Model theory investigates categoricity and saturation properties. Advanced areas include stability theory, O-minimality, and non-standard models of arithmetic, higher dimensional algebra, and n-categories. Higher dimensional algebra extends category theory into multiple levels of abstraction. It introduces morphisms between morphisms. While ordinary categories have objects and morphisms, two categories add two morphisms between morphisms. Its foundations include bicategories where laws hold only up to isomorphism, double categories, and n-categories for arbitrary dimensions. In the two category of categories, objects are categories, one morphisms are functors, and two morphisms are natural transformations. This creates a three-tiered structure. The framework formalizes concepts like higher homotopies. Advanced topics include quasi-categories, opereds, homotopy-type theory, and derived algebraic geometry. They are impossible to visualize yet essential for modern mathematical theories. Functional analysis studies infinite-dimensional vector spaces, particularly spaces of functions, and linear operators between them. It generalizes linear algebra and provides rigorous foundations for quantum mechanics and differential equations. Its core objects include Banach spaces, complete normed vector spaces such as L raised to P spaces, Hilbert spaces, complete inner product spaces generalizing Euclidean space, bounded linear operators and their spectra, weak and strong topologies, and dual spaces consisting of continuous linear functionals. Key theorems include the Hahn-Banach theorem on extending linear functionals, the open mapping theorem and closed graph theorem, the uniform boundedness principle, the spectral theorem for self-adjoint operators, and the Riesz representation theorem. Advanced topics include operator algebras, C-star algebras, distribution theory generalizing functions, and Sobolev spaces. Functional analysis bridges pure mathematics and mathematical physics. Algebraic geometry studies solutions to systems of polynomial equations, called varieties, using tools from commutative algebra and category theory. It unifies algebra and geometry, allowing geometric intuition to solve algebraic problems and vice versa. Its foundations rest on affine varieties, defined as zero sets of polynomial ideals, projective varieties, which compactify affine varieties by adding points at infinity, morphisms between varieties, structure sheaves providing local algebraic data, and schemes, which generalize varieties and allow nilpotent elements. For example, the affine variety V of I in affine n-space over K consists of all points where polynomials in ideal I vanish simultaneously. Central concepts include dimension theory, Hilbert's Nullstellensatz connecting ideals and varieties, coherent sheaves and their cohomology, divisors and line bundles, and intersection theory. Deep results include Bézout's theorem on intersection multiplicities, resolution of singularities, Riemann-Roch theorems, and Grothendieck's schemes revolutionizing the field. Noncommutative geometry extends geometric concepts where coordinates don't commute. This means xy not equal to yx, fundamentally altering space and measurement. It replaces function algebras with non-commutative algebras. These are treated as functions on generalized geometric spaces. Its foundations include C-star algebras, K-theory, cyclic homology, spectral triples, and index theory. Advanced areas include non-commutative differential geometry, quantum groups, and applications to foliations. This allows treatment of singular spaces that resist conventional geometric analysis. Categorical homotopy theory merges category theory, topology, and algebra. It studies spaces and structures in settings of extreme generality. It replaces point set topology with abstract homotopy theories. Its foundations include model categories, simplicial sets, infinity categories, operads, and derived functors. Advanced topics include stable homotopy theory, ring spectra, topological modular forms, and chromatic homotopy theory. These constructions exist several layers removed from explicit computation. They reveal unity in mathematics invisible at lower levels of abstraction.